This lesson builds up on the previous lesson where we introduced the concept of difference in means hypothesis test. We lay down the steps and formulas involved in the test. We also introduced two variations of the test wherein we need to assume the population variances of the two populations from where the samples come to be either equal or unequal. We will continue from where we stopped in the previous lesson. We wish to test the claim that the difference between the population mean height between men and women Olympic athletes is 12.5 centimeters. Recollect that the empirical study had come up with an average difference of 12.5 centimeters in heights of men and women from various walks of life across the world. We wish to test whether this claim also holds for the population of Olympic athletes. Step 1 of doing the hypothesis test is framing the null and alternate hypothesis. The null hypothesis here is that mu men minus mu women is equal to 12.5, where mu men is the population mean height of men athletes at the Olympics and mu women is the population mean height of women athletes at Olympics. That is the average height across all women athletes who have participated in any Olympics. The alternate hypothesis then becomes mu men minus mu women is not equal to 12.5. This is a difference in means test because we wish to test the claim about the difference in the two population means. Further, this is a two-tailed test because there is an inequality in the null hypothesis. Thus, when translated onto a t distribution, the test will have two rejection regions, one on the right and other on the left hand side. Step 2 of the hypothesis test procedure is to calculate the t statistic. This is where things get a bit more complicated as compared to the single population hypothesis test. To calculate the t statistic, you first need to make a determination of the nature of variation in the population from where these two samples are drawn. In particular, we need to consider whether the variation or spread in the population data across the two populations is likely to be similar or dissimilar. In other words, you need to either assume that the population variances for the two populations involved are equal or that they are unequal. Remember, you do not know the population variances or the spread in population data. So, assuming equal variance or unequal variance across the two populations becomes more of a thought exercise. Though there are some statistical tests that help you in the process of figuring out whether the population variances are likely to be similar or dissimilar, we will not be getting into those tests as the additional value in knowing those tests to business applications is minimal. So, we will do a subjective judgment in either assuming equal variances or unequal variances across the two populations from where our samples are drawn. Though looking at the sample variances from the two samples that you have may give some indication whether the population variances are more similar or more dissimilar, nevertheless, this is still a subjective judgment to be made by you. In this case, I would tend to argue that the variation in heights for the population of men Olympic athletes is likely to be similar to the variation in heights of women Olympic athletes, as they both belong to the competitive sporting profession and have emerged at the Olympic levels after a tough selection process, indicating that there are more of similarities than dissimilarities in the variation of heights. Thus, we would assume equal variances across the two populations. Notice this is a very subjective judgment. For example, some of you may argue that men and women are inherently different and hence the variation in heights is also likely to be more dissimilar, thus arguing for an unequal variance assumption across the two populations. That too is a reasonable argument and cannot be falsified. However, as you will see in subsequent lessons, in most applications this argument of equal versus unequal variances is more of an academic argument, and in terms of results of the hypothesis test, your conclusions really do not change. So, if in doubt, you may as well flip a coin and either assume equal variances or assume unequal variances. The t statistic, when variances are assumed to be equal across the two populations, is calculated as shown. X1 bar and X2 bar are the two sample means, X1 bar for the average height of men athletes in our sample, and X2 bar the average height of women athletes in our sample. Mu is the difference in population mean around which you wish to test the hypothesis. N1 is the number of men athletes in the sample, and N2 is the number of women athletes in the sample. Note that the two sample sizes need not be equal. S1 is the sample standard deviation of the heights of men athletes in our sample, and similarly S2 is the sample standard deviation of the heights of women athletes in our sample. So, this is the t statistic calculation in a difference of means test when you assume population variances to be equal across the two populations. When the assumption on the two population variances is that they are not equal, then the t statistic calculation takes a slightly different form as shown, where the various expressions such as x1 bar, x2 bar, s1, s2, n1 and n2 have similar interpretation as in the equal variance assumption case. Fortunately for us, Excel has an inbuilt data analysis add-in that will take care of these calculations for us. In the next lesson, we will introduce that add-in and complete this hypothesis test.